Greetings. In this session, we'll be discussing about how to use electric binary. We'll be not using SPICE for simulating this. In electric binary, we have an inbuilt tool, ALS. We'll use it for generating waveforms. We'll be discussing about inverter, common source, and common drain. Okay. We'll first go through the installation, which is not a requirement. First, go to the drive where you have saved the electric tool. For easy access, I have saved it in my C drive under a folder called electric. Okay. For my Windows, I'm using electric binary 9.07. As you can see, this is a jar file. Jar file means it is a Java executable file. Means we don't have to install anything. If Java is installed on the PC, that is well enough. To check whether Java is installed or not, we have to go to Programs from the control panel. Most systems nowadays come with Java installed. We just confirm it. It's loading. Okay. Here I have a Java 7 and Java 8 is also there with a SE development. Okay. And this LT Spice we are not using in this session. If Java is not available or if Java is not working, there's a simple solution. We can go to the Java website and either download online or you can copy a offline executable file. No need for registration or logging in. We have all the options. If yours is a 64-bit PC, you have to install this offline. If 32-bit PC, you have to install this offline. Online is you should be connected to the internet. Okay. Once we download this offline file, we have to double click. It will install the Java. If there is any error with the Java, uninstalling and reinstalling Java using these is a very good option. To understand what is the version of Windows we are using, we have a command winver in the command prompt. We can see we are using Windows 10 here, and if you go through the properties of our PC, you can see the version of Windows. So assuming that we have installed, I'll start the tool once again, starting from the folder. I'll close this. So assuming our setup is done, means electric binary is ready to execute because of the Java availability. We'll start the session from here. Double click electric binary, the tool should load. Okay. This is our window where we are going to design the things. This window called as electric messages is for saving the errors, and like we can observe, a file is created, log file, in the directory where we have our tool. This is our exact directory where we had saved our tool, C drive electric folder. In this window, here we'll be seeing the components, Explorer, layers. Layers is for layout. Explorer is where we will see all the projects we are doing, the files what we are creating, the cells, and even the errors. Okay. We'll start with checking whether our setup is perfectly ready for designing. Go to File, Preferences, Technology, scale. This is MOCMOS 200 nanometers. If 200 nanometers is not available in your version, 180 nanometer is most famous. So this can be used. This is first thing what has to be checked. Under general, this should be 512 megabytes. If this is a small allocation on your PC, you can check whether it is large enough to accommodate our large files. Then under tools, Spice CDL. If we are using LT Spice, this should be available, or else run and ignore output is sufficient enough. Okay. This is for Spice. If we write Spice code, all these are necessary. I'll close this. No need to be changed. Only change what we have to do is run and ignore output. So everything is set. First we'll start with a library, file, new library, and give a name, select inverter, can be anything. Okay. For easy access, I will save this library. Easy access means I should be able to find my library and its associated files. I'll go to the electric tool, create a new folder where I will save this inverter. Okay. Open this folder, save, means now our library is saved in C electric folder, under that inverter folder where we'll have a Java lib file library, and it is observed here. Inverter is added as a library. Next is for creating schematic, click on cell, new cell, select schematic, give a name, anything, I'll write INV, say OK. Once we say it's a schematic, the components will be PMOS and NMOS. Schematic of PMOS and NMOS. When we go for layout, these will automatically change to layers. I will take NMOS, I will take PMOS, will require supply, click, move the mouse, click, placed, ground, move the mouse button, click, placed, pins, click, placed, another pin for output, click, place. Now these are very small for our observation, so we can view it in a better way. Go to window, fill window, this will be large enough. I'll make it still larger, window, fill window. Okay. We'll use the standard MOSFET size. I pressed Control plus I. Control plus I is the keyboard shortcut to change the values. I'll keep the value of PMOS as 10/2, W by L ratio 10/2. Say OK. For NMOS, Control I. Sorry, Control I, 10/2. Okay, same sizes. We'll not worry about the sizes right now. We'll just try to see whether our simulation happens with the proper waveforms. Okay. For making the wires, left click on the start point, right click on the end point. This should get connected. Same way, left, right, left, right. Short the gates, left, right, left, right, left, right. Okay. So this completes our inverter schematic design. We have to check if there are any errors. For checking the errors, click on Tools, DRC, check hierarchically, F5. If you find any errors, click on OK. You can reduce the size of this window. It was earlier maximized. Click on Restore. Window will become small. Check on the electric messages. There are 2 errors. To view the errors, we have to go to Explorer, errors. In the schematic INV, it is saying points are not connected, some problem with the points. Arc dangles means where there is a wire connection problem. Okay, we'll just try to replace PMOS. I'll just delete it. We'll take a component called PMOS, place it, we'll wire it once again, delete, left click, right click, left click, right click, left click, right click, save it. Excuse, I'll press F5, no errors. Instead of searching the exact error, what I did is I just repaired the PMOS and did the connections once again. Now we can see that 0 errors, 0 warnings. So this is ready. Next what we can do is we can put some names for this. How to put the name? Export it as VIN, press Ctrl plus E, E for export. Name it as VIN. Don't do any changes. Press OK. This will be named as VIN. Select VOut. Whenever we select a component, it should be highlighted by a big box. Then only it is meant to be selected. Again, press Ctrl E. Name this as VOut. Say OK. I'll press Ctrl 9 to fill the window. Or we can go with window, fill window. Next is, once we have our schematic ready without any errors, we'll try to simulate it. Go to Tools, Simulate Built-in ALS. So we have all the possible waves here. What we have to observe is VIN and VOut are to be opposite. VOut is inverting of VIN. There will be a small delay here because of the characteristics of PMOS and NMOS. We'll ignore this delay, but we can observe that VIN, I'll just expand this wave, VIN is 0, VOut is high. Okay. For changing the values, click on VIN, click here VIN, press V, V for voltage on the keyboard. This wave should go high. Let's press V. Okay, neat enough. Pressing V, this wave got high, this wave got low. Means this is our inverter output. Sorry. Same way, we'll move this dotted line. Means we want to give another value at this part, at this point. How to do? VIN should be selected. Press G, G for ground. Okay, so this is grounded, but still output is again inverting, means it is perfectly working as an inverter. This is our output, which is opposite of input. So this tells us that our schematic for inverter is running perfectly on electric binary. Okay, I'll just close this. We'll start with another view of this cell. We'll not create a new library. We'll just take a new cell, name it as again INV, but this time we'll try to say it as a layout. Okay, so our earlier window is gone. Now we have our layout screen. Where is our earlier window? Under Explorer, if we expand inverter INV, now it has many views. One is schematic view. Double click, you will see schematic. The one we are doing right now, layout, LAY, which is blank. This is where we have to create our layout. Layout, schematic we have done and simulated. Go to components, use PMOS, use NMOS. For providing source and drain, use PACT. For PMOS, on either sides, source drain, enact for NMOS, either side, source drain. We'll use a safe value. Like I said, we'll not worry about the exact sizes. Control I, we'll use 10/2 for PMOS, for source and drain. Again, 10/2. Control I, 10/2. Control I, 10/2. Same way here also. Control I, 10/2. Now our MOSFETs are to be ready. Once we provide source and drain connection to this, we'll make it look neater. Our conventional inverter, how to do is rotate this, click, edit, rotate clockwise or anti-clockwise. I will use anti-clockwise because it has a keyboard shortcut, Control J. Okay. Click, selected, Control J, rotated. Click on this center, Control J. Click on this, 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 Control J. This is looking smaller. Maybe we did not edit its W by L. I can edit now. 10/2. Okay. Now these are neat enough. We'll place them sufficiently far apart. We're not following the rules, but if any errors are there, we'll just try to clear them. We'll place this exactly one below the other to see if our poly to poly connection is simple enough. Let's observe by zooming in. For zooming in, Control +7 and move. Okay, so these are perfectly aligned. Control +0 is zoom out. So I'll just bring this NMOS back down. Next is the connection. Left click here, right click here, left click here, right click here, left click, right click, left click, Control Z to undo, left click, right click. Next what we'll do is we'll move this and try to overlap until we don't have an error. Select, move it near. We can observe the mouse button. At this point it is showing error, so we should not place here. We should place one step before the error. What we'll do is we'll check whether this design is correct. Few errors are there, we'll check after placing these enacts on NMOS. Error, no error. Okay, let's see. 8 errors are there. Again go to Explorer, check errors. We want our layout errors, current one. Click here, minimum size. Of enact is less than 2 in size. Okay, seems like 2 is not a valid size. Let's see if we can work with 10/5. I'll change everything to 5. We'll take the enact. Sorry. Maybe because these are connected, they are auto correcting themselves. Let's see if this generates any errors. Okay, still not any errors. I'll just remove everything and redo it. 10/5 components, PMOS, NMOS, NACT, PACT, PACT, control I, 10 by 5, 10 by 5, 10 by 5. Once you know the keyboard shortcuts, these are easy enough. 10 by 5, control 10 by 5, rotate, control J, control J, control J, control J, control J, control J, align them, align, align, align. I use the mouse keyboard keys, cursor keys to align them up, down, connect, connect, left, right, left, right, left, right. I will use the keyboard key to move. I'll stop at this place. Here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Okay. Seems good enough. We'll move this also. This near. This near. Okay. I'll press F5. No errors. Okay. So 10 by 5 is a good number. We'll use 10 by 5. I'll just move these things. Select all by drawing a rectangle on this. All are selected. Move up. Up, save this, gate to gate connection for inverter, click here, left click, right click. Okay. Small connection, let's see if it works or not. Okay, it works. I pressed F5, no errors, no warnings. So once we have this, for NMOS, we have to use a P-well here. For PMOS, we'll use a N-well here, substrate connections. We'll not look into the theory. We'll try to connect this, left click, right click, left click, right click. Seems very good connection. Let's check for errors. Function F5, we are seeing one error. Let's see the error. You have to always see the current errors here. Minimum width is less than 12 wide. Okay, maybe it is asking for bigger N-well. P-well is okay. N-well can be made bigger. We'll use again our earlier standard 10 by 5. Let's see function F5. 0 errors, 0 warnings. Just for beauty's sake, we'll expand this also. Completely unnecessary, just for beautification. Function F5. 0 errors, 0 warnings. So let's go to go. I'll press Control 9, fit to window, short the drain to drain. There should be no errors. Function F5, again 0 errors, 0 warnings. Just for beauty's sake, we'll extend this to the right, left click, right click to the left, save, function F5. So 0 errors, 0 warnings. We can export these and run our signals. Let's see, click here, press Ctrl E. This connection should be given with a power, we'll call it as VDD. We selected this N-well part node and gave it VDD. I'll do once again, Ctrl Z, select this node, Ctrl E, VDD, export characteristic should be power, say OK. Here at the bottom, P-well, Ctrl E, VSS, this should be ground, OK. Input side, gate shorted, Ctrl E, VIN, this should be input, export characteristic, input. Okay, click this, Ctrl E, V out, output signal. Select here, output, say okay. So now all our signals are applied. Let's check once again. F5, no errors, no warnings, we are good to go. Go to tools, simulation, ALS. Let's check whether this is our inverter. Select VN, press V, high, low. Move this tracer, move this dotted line, press G, ground. This is high. So our layout is good enough. So this is about our inverter layout. In the earlier part, we completed our inverter schematic where we had our same results. So we'll go to our next cell. We'll keep everything as it is. If you want, we can create an inverter folder. Maybe good enough. We'll just close this library. We'll save everything. Yes. And we'll start with a new library. We'll make a new folder for this. New library, common source. Okay. We'll save this in a new folder. Not under inverter. We'll save it in a new folder where C drive, electric, new folder, common source. Okay, open, save. Common source is saved. Cell, new cell. We'll just call this as CS schematic. Say OK. Components. For common source, we will be requiring PMOS, NMOS, supply, ground, pin, control 9, fill to window, size, we'll go with 10 by 5, control I, 10 by 5, connect these, left click, right click, left click, right click, left click, right click, left click, right click, left click, right click. Okay, care should be taken that PMOS is to be grounded. Left click, right click. So this is our common source design. We'll name this as VA characteristic. Keep it as unknown. Okay. Control E, V out, unknown characteristic. Done. Save this. This will act as our resistor. This is shorted and it will be biasing the circuit. VIN is applied at the gate. V out is taken from the drain. So this is our common source amplifier. This tells this part is source, which is common between VIN and V out. We'll try to simulate this. Go to tools, check once if any errors, no errors. Simulation, ALS, select VIN, press V, output is decreasing. Let's see whether it will run for second time. I'll just expand this window. Common source is inverting configuration. So if we give a high, output should go to low, which is happening. Select VIN, let's give a ground. It's working. Let's try to put a value here. We'll trace here. Select VIN, press ground. Output should have increased. Some problem. We are not seeing this increase for common source, but again, this will tell us, this part tells us it is operating as an inverting configuration. Okay, this is our common source schematic. We'll try for our layout. Cell, new cell, CS, layout. Okay, we'll take our PMOS, NMOS, PACT for PMOS, NACT for NMOS. We'll save the changes of style 10 by 5. 5, 10 by 5. Sorry, we should have used some practical values, but for just simulation purposes I am not worried about the sizes right now. 10 by 5. Okay, rotate. This should not give any errors because we did same sizes for inverter. Okay, move them until there is no error. Move, close enough. Okay, I'll save this. F5. Let's see if any errors. I'll close this window. 0 errors, 0 warnings. So we'll keep continuing. Take PWell, put it on nearby NMOS. Take NWell, put it above PMOS. We know that size has to be changed. In inverter we got an error. So I'll keep this as 10 by 5. This is not necessary for PWell, but still we'll try to change it as 10 by 5. Okay. Let's make the connections. We'll not short the. I'll just move this. I have selected all the components by drawing a box. Press down and key on the keyboard. It will move further because we have to make a connection from gate to drain short. I have moved this apart. Click here, connection for beauty. Click here, done. Save. This will be provided with input. This has to be connected to VDD. What I did, left click here, right click on the metal, it will get connected. The wire required to connect polysilicon to metal will be auto generated. This is auto generated. Again, let's check if any errors. Function F5. Few errors are there. One inexact. Let's see what is the error. Minimum width. Okay. Let's check once again. I just moved it. Okay, more errors. Some notch is being created. I'll just delete. Try to put what once again. We'll take NWell, place it here. I'll just zoom here by pressing Ctrl 7. Ctrl 0 to zoom out. Just align these. Okay, these are aligned. I'll move it up. I'll press Ctrl I, make this as 10 by 5. Let's try to connect. I'll align once again so that no notch is created. Notch is one where our metal is not in perfect triangle shapes. Okay, these are not perfectly aligning. I'll try to move the mouse. Some problem. Let's see. Left click, right click, function F5. Still errors are there. Ctrl 0. NWell, place function F5. 7 errors. One error. Ctrl I, 10 by 5. Okay, no errors. Means just some trial errors to see what will work. 10 by 5 worked, and with this placement. Okay. This placement, I'll just Ctrl 9. This is our layout. Tools, check hierarchy, no errors. Built-in, simulate. If we simulate with this as V out, Control E, V out, as output. Node has to be exactly selected, so this is not taking OK here. It is saying here must select a node. So I'll select a node, Control E, V out as output. Still not selected. I'll click carefully here, exactly on the node, or you can take here also. Node is selected. Control E, V out, output type. Here will be applying. Control E, V in, input type. This is Control E, power, VDD. This will be Control E, VSS, ground. Okay. Tools, simulate, V in. If we make it high, output should go low. Something is not right. We'll ignore the output. Anyway, we don't have errors in the layout. V in is not making any difference on the V out. Let's ignore this. We are ready with our layout with no errors. Function F5, 0 errors, 0 warnings. Okay. Let's go with a final design of common drain. New cell, under a new folder, new cell, schematic, CD. Okay, what I will do is, we have all the designs ready. I'll just save this library in a new folder under C drive, electric folder. Right click, new folder. I'll call this as common drain. Open, save. New cell we have ready with a schematic. What I'll do is, I'll copy our common source design, schematic, copy. I'll paste it to our common drain schematic, paste, place somewhere. This should be removed. We'll add a NMOS. This is our design of common drain. Put an NMOS. V in should be connected to the top NMOS. I'll just delete this and place. We'll use 2 pins, 1 pin, another pin. You can draw these things separately also for saving time. I'm copying from the common source. Seems good enough. We will name this as V in, unknown characteristic, VB, unknown characteristic, V out, unknown characteristic. Function F5, 1 error. Maybe I'll remove this connection and connect once again. Delete, connect. Function 5, no errors, 0 errors, 0 warnings. We'll try to simulate this with the values which are already there. V in, if it is high, output goes high. We are not worrying about V bias. V in is made high, V output will also go high. This is our common drain. Let's see if it works for ground. Ground, second time it's not working, but this is close enough. VDD, when supplied to V in, output also goes to high. I'll just remove this. How to do the layout? We have to use NMOS on either sides. I'll again go to our common source. I'll take the layout from common source, copy, common drain. We'll make a new cell. We'll call this as CD layout. Okay, paste. Okay, I'll just fill it for the window. Control 9. Expand this. We know what are the changes to be made. We don't require PMOS here. Okay, sorry. Okay. And this also. We'll take a component of NMOS once again with the NAT and NAT again. We'll require two NMOS. Control I, 10 by 5. Control I, 10 by 5. Control I, 10 by 5. Control J, Control J, Control J. Keep them as nearby as possible. Make a connection. Left click, right click, left click, right click. Overlap, not aligned. We'll align these. Okay. We'll try to move the NMOS and see if the alignment is proper. No. So we'll try to move only the this back. I'll select only these three things and move it. Let's hope these are connected. Again, Control 9, fit to window, click here, connection, click. Will not be connecting this to this. This requires Control E, V in, unknown characteristic. This requires Control E, VB, unknown characteristic. Control E, V out. Sorry, for layouts we should follow the characteristics. V out. This will be VLSI of ground type. This will be VDD of again power type. We'll try to see if we can edit this. VN, whether we can change the characteristic. Yes, we can. VN input type. Okay, updated. Same way we'll try to change V out. Sorry, VB. VB is also input type. Control 9, fit to window, function F5. One error is there. Let's check. CD, latest errors, minimum width. Okay, this is creating some problem. We'll just delete it. Okay, because this is NMOS, it will require PWEL. We have to place a PWEL. Control I, 10 by 5. Connect. Function F5, no errors. Okay. This tells that the layout is ready. Further, we'll see if it can generate the waves. V in, select, make it high. Output should have gone high. It is not happening. Some problem with the waves. Let's ignore this. Our layout is ready. So in this session, we completed observing common drain, common source, and inverter. Okay. So thank you. If you have any doubts or clarifications, you can leave a feedback or comment. Thank you. Happy learning.